This is Dr. Joseph Ansong. Thanks for coming to this channel. Today we'll take you to a calculus class. We want to look at things like the integration of exponential and logarithmic functions. We'll also look at indeterminate forms and L'Hopital's rule. So make sure that you subscribe to this channel, make sure you like it, and then leave your comments. That will help us a lot. So if limit as x goes to a of f of x is equal to, let's say 0, and the limit as x goes to a of a function g of x is equal to infinity, then the limit as x goes to a of, say, f of x times g of x will give us something like that, and we'll set to be indeterminate. Okay, so that gives us an indeterminate form. Or 2, if the limit as x goes to a of f of x, this is going to infinity, and then this is also going to infinity, of g of x is going to infinity. Then when we take the limit as x goes to a of, let's say, f of x minus an expression for g of x, we're going to have something like infinity minus infinity, and that is also indeterminate. And so how you solve these ones are that you turn them, okay, when you have a form like this, you try to turn it to a form like 0 over 0 or infinity over infinity, and then you can use L'Hopital's rule that we've seen before to solve them. Okay, so they are not very different. You just have to manipulate the expression that you have and put it in a form so that you get a 0 over 0 or infinity over infinity. So let's look at these examples. Want to evaluate, I have a, the limit as x goes to infinity of x squared sine of 1 over 4x squared. And then I have another expression, limit as x goes to 0 plus x ln x. C, let's try this one, limit as x goes to infinity, x minus the square root of x squared minus 3x. Okay. All right, so let's do these ones. You can do all 3, or let's say 2 of them, and then you can try one for yourself. Okay, so here you have the first one is this. I have the limit as x goes to infinity of x squared sine of 1 over 4x squared. Okay? Okay, great. Now notice that as x goes to infinity, this guy goes to infinity. As x goes to infinity, all of this goes to 0. Sine of 0 is 0. So this guy is going to 0. So you have the form 0 dot infinity, or infinity times 0. So that is the form that you get, okay? If you just do it directly. Because it's of this form, you can rewrite it. So rewrite it so that it looks like a fraction, like a quotient. Okay, so you can rewrite this to be the limit as x goes to infinity. Okay, so let's try to do it this way: sine of 1 over 4x squared divided by 1 over x squared. Okay. So that this is the same as that. Now as x goes to infinity, we're going to get 0 up here. Okay, 1 over x squared also gives us 0. So now we have the form 0 over 0. Okay, and so because we have a 0 over 0, we can directly apply L'Hopital's rule to it, which means we differentiate this and also differentiate this, and then plug in our expression, the limit, to see what we get. All right, so let's do that. So using L'Hopital's rule, we're going to have limit as x goes to infinity. Okay. Now, want to differentiate what is in here. So if you differentiate 1 over 4x squared, know that this is 1 over 4x to the negative 2. Okay. So this is basically negative 2 over 4x to the minus 3, right? So this is minus 1 over 2x to the negative 3. All right. When you differentiate what is in here, that's what you get. So you differentiate that, you're going to have minus 1 over 2 x to the minus 3. Okay. When you differentiate sign, you get a cosine. So that is cos of 1 over 4x squared. Divide this by. Now when we differentiate this, note that this guy is x to the negative 2. So this will give you negative 2 x to the minus 3. So negative 2 x to the minus 3. That is okay. So this is what you get. Note that you have x to the negative 3 here. X to the negative 3, they cancel out straight away. You have negatives that cancel out. Okay. And so we have simplified our expression. So let's do this. So from here, let's go over here. Let's go over here. We know this, so we can do this later. So we have. So this implies. So this is equal to the limit as x goes to infinity of. Okay, because these guys cancel out and the negatives cancel, I'm just going to have 1 over 4 here, and then cosine of 1 over 4x squared. Good. So now, watch this. As n goes to infinity, I'm going to have a 0 here. Cosine of 0 is 1. Okay, so this guy goes to 1 over 4. All right, so that gives us, using L'Hopital's rule, that expression. Okay. Now B says we want to find the limit as x goes to 0 from the positive side, from the right side of x. I think it's x in x. Okay. Now note that as x goes to 0, this is going to 0. All right. What about this guy? As x goes to 0 from the positive side, remember lane is this guy here. It looks like this. This is 1. Okay. So as you're approaching 0 from the right hand side, the lane function is going to negative infinity. You see? So this is negative infinity, that is 0. So you have the form 0 times infinity. Okay. So again, because it's of that form, you try to turn it to the form where you have a 0 over 0 or infinity over infinity, and then try to solve it. All right. So from here, you can rewrite this as the limit as x goes to 0. Let's see. So you can write this as ln x all over 1 over x. Okay. So now as x goes to 0, this guy is going to negative infinity. This guy is also going to infinity. So now you have infinity over infinity. So you can apply L'Hopital's rule. So we are going to get the limit as x goes to 0. The derivative of then x is 1 over x. The derivative of 1 over x is negative 1 over x squared. Okay. We can simplify that. This is the limit as x goes to 0 plus, okay, note that this is just minus x. All right, this is just negative x because I have 1 over x, and then x squared comes up here. All right, so the x cancels 1 over x's, so I have minus x here. So this guy is going to 0. All right, so finding the limit of this using L'Hopital's rule, first of all, turning it into this form gives us a limit of 0. All right, good. So you could try the third one. So that we'll finish off with the last bit of indeterminate forms. Okay, so the last bit of indeterminate forms has to do with expressions which say 0 raised to the power 0, 1 to the power infinity, and those kinds of indeterminate forms. So we're going to finish off with this kind. We have indeterminate forms 0 raised to the power 0, infinity to the 0, 1 to the power 0. Okay, so we want to find, so this occurs if you have limit of x going to a of an expression, let's say f of x raised to the power g of x, if you have these forms. Okay, so this is indeterminate, so the expression, okay, this expression is indeterminate if, okay, if first of all you have limit x going to a of f of x, if this is going to 0 and limit as x goes to a of g of x is equal to 0, then we have the form 0 to the power 0. This is going to 0, that's also going to 0. Okay, so what does the whole expression approach? That is the question. Okay, so you end up with these. Again, if for instance this guy is going to infinity and this is going to 0, right, then you have this form. If f of x is approaching 1, but this guy is approaching infinity, then you have the form 1 raised to the power infinity. You have these three forms of indeterminate. Now there's a very nice trick to solving these type, okay, using logarithms. Okay, so what you do is that, so if you like solution procedure, solution approach, okay, so what you do is that you let, let's say y equal to your function f of x raised to the power g of x. Okay, then you take the lane of both sides. You have lane y is equal to g of x, lane of f of x. Okay, so this is what you do now, and then take the limit of both sides. So take the limit as x goes to a of lane y is equal to the limit as x goes to a of this guy, g of x, lane of f of x. Okay, suppose that this guy is equal to some L. Okay, the right hand side is equal to some number L. Okay, if that is the case, so this implies that limit as x goes to a of lane y is equal to L. Now when you get here, there's a nice trick to use in order to get your y back. Because lane is a continuous function, you can take the limit inside in here, okay, and pull the lane out. And so you can rewrite this as the lane of the limit as x goes to a y is equal to L. Okay, note that lane is the log to the base e. So this implies that this thing here is equal to e raised to the power L. Okay, so this implies that the limit as x approaches a of y is equal to e raised to the power L. Okay, now remember that y is our original function, okay, that we had over here when we started. So that implies that the limit, so let's come back here. Okay, so this implies that the limit as x goes to a of y, and y is f of x, g of x, okay, is equal to e raised to the power L. Which means that to find the limit of these forms, the most important thing is how to find this. Once you get this, then you have a solution. Okay, so you need to be able to solve. Okay, so the main problem to solve is solve the limit as x goes to a of g of x, lane f of x. Once you have this, then you're basically there, because you have e raised to the power of that. and that will give you your limit. Good. So that is about these forms. So let's do some 2 or so examples to illustrate this, and then we'll be done with indeterminate forms. Okay, so let's do some examples. Look at this. Let's see. All right. So here I have evaluate. I have the limit as x goes to 0 plus x raised to the power x, and I want to find the limit as x goes to 0 plus let's say 1 over x raised to the power sine x. Okay, so let's do these ones. All right. Okay. So solution. Okay. So for A, let's see. Okay, so for A, we want to find the limit as x goes to 0 plus x raised to the power x. All right, so again, we're going to this is the procedure for this type. Well, note that as x goes to 0, you're going to have 0 and 0. So this is of the form 0 to the power 0. So it's indeterminate. So we can use this procedure. So let y be equal to x raised to the power x. Then the lane of both sides will give you x, lane x. All right. And so now we can take the limit. Okay. So now the limit as x goes to 0 plus of lane y is equal to the limit as x goes to 0 plus x, lane x. Come across this already, because as x goes to 0, this is a 0, but this is going to negative infinity. Okay, so again, as we did before, we turn this into that form. So you're going to write this as limit as x goes to 0 plus write this as lane of x all over 1 over x. Okay, so we have the limit as x goes to 0 plus, well, this is infinity, so differentiate this, that is 1 over x. And this guy is negative 1 over x squared. Okay, and then we saw that this one is going to 0. All right, so this is saying that what this is telling us is this, that the limit as x goes to 0 plus of lane y is equal to 0. All right, good. Again, because lane is continuous, we can rewrite this as the lane of the limit as x goes to 0 plus y. This is equal to 0. This implies that lane is log to the base e, so it means all of this is equal to e raised to this power. So the limit as x goes to 0 plus of y is e raised to the power 0. And e raised to the power 0 is 1. Therefore, the limit as x goes to 0 plus of y is our original function, which is x raised to the power x, is equal to 1. So the limit as x goes to 0 from the right of x to the power x is equal to 1 from these. Okay, good. So let's finish off with the last example. The last one says let's find, so this b for b, we want to find the limit of 1 over x raised to the power sine x. Okay. Okay, so let's again the same procedure. Well, here you see that as x goes to 0, we're going to have infinity here. Okay, we're going to have 0 here. So this is infinity to the power 0. So that's this type, infinity to the 0. And so we're going to let y to be equal to 1 over x sine x, as we did before. Similar procedure. Take the lane of both sides, and the lane y is equal to sine x lane of 1 over x. Then take the limit. So limit as x goes to 0 plus of lane y is equal to the limit as x goes to 0 sine x lane of 1 over x. Okay. All right. So you're going to have as x goes to 0. Note that this guy is going to go to 0, right? S goes to 0, so you're going to have infinity. As you go to infinity, lane is going to infinity. You're going to have 0 and infinity. So it's similar to what we've seen before. So the plan is that you rewrite this in a way that you get a 0 over 0 or infinity over infinity, and then you can do the derivatives. So that is the plan for that. So here we can rewrite this to be equal to the limit as x goes to 0 plus, this is, we're going to have ln 1 over x, all right, and then this we can rewrite as 1 over sine x. Okay. So now as x goes to 0, all right, this guy is going to infinity, that is also going to infinity. So you can do the derivatives, find the derivatives of both sides. So let's do that here. Okay. All right. So to we want to differentiate this guy here. So the derivative of what is in there is minus 1 over x squared. All right. That is the argument, right? Note that if you differentiate, when we differentiate ln of x, you're going to have like 1 over x, right? So you always have 1 over x, and then multiply by the derivative of what is in the argument. Okay, so 1 over x is just x, so you're going to have x here. All right, so again, limit x goes to 0 plus all over. Now we're going to do this one. 1 over sine, right? 1 over sine x. You want to differentiate this one. You can use the product, the quotient rule, right? If you want, leave this guy, sine x, differentiate this as 0, minus, leave this, differentiate this, that is cosine of x, all over the square of this, which is sine squared x. So basically you have negative cosine of x all over sine squared of x, right? Okay, so you get this. So down there, you're going to have minus cos x all over, you have sine squared of x. All right, so this is equal to the limit as x goes to 0, positive, well, the negatives cancel. I have 1 over x up here. I'm going to have cosine of x all over sine squared x. Okay, good. So now we have, as x goes to 0, we're going to have infinity over here. As this goes to 0, this guy is 1 over this, so we still have infinity. All right. Okay. So what you can try to do is that you could go through the same process again, right? you find the derivatives, the derivative of the functions again. Now, it's important to know that this from here, it's important to know that here, whatever you bring to the bottom matters. It's very important. If you bring, we could have left sign here and then brought down 1 over ln of this, okay, or could have done it the other way around. Depending on how you do it, you could get a solution or you could go on forever and ever. Never get the solution. So let's see how this one works out, right? If we go ahead and find the derivative again, okay? So if you go ahead and find the derivative again, we are going to have lim, so we're going to have limit as x goes to 0 plus, the top will just give us minus 1 over x squared, okay? What does the bottom give us? Actually, this is, okay, so this is cosine of x all over sine squared x. Okay, so hold on. So this is we can rewrite this as 1 over sine squared x all over x, cosine of x. Okay. Yeah. So this is better. Let's see. So this is limit. So that is from here. Limit as x goes to 0 plus of, okay, as we go to 0, that is going to 0. This is 0, this is a 1, so 0 over 0. So differentiate this. This is 2 sine x cosine of x. This is products. That will just be the cosine of x. Leave x. Differentiate this. That is minus x sine of x. All right. So let's see. So this is equal to, this is 0 limit as x goes to 0 plus. We're going to divide through as x goes to 0. So what do we have now? We have 1 here. We have a 0 here. This is a 1. That's 0. Okay. So it's going to 0. All right. You see why? As x goes to 0 plus, okay, this guy is 1, 1, right? This is 1, this is going to 0, right? So you have 0 here. This guy is 0, but you have 1, okay? So you're going to have 0 over 1, okay, which is 0. So this, from here, we can conclude that this is going to 0, okay? Good. Now, this is going to 0. What it means is that if you go all the way back, okay, all the way back, we said that the limit as x goes to 0 plus of ln y, this is equal to 0. So similar to what we did before, you can pull out ln. You have the limit as x goes to 0 plus, okay, of y is equal to 0, which implies that, okay, limit as x goes to 0 plus of y is equal to e raised to the power 0, which is 1. So that limit as x goes to 0 plus of y is the expression 1 over x raised to the power sine x. Okay, it's equal to e to the power 0, which is equal to 1. All right. So it's the same thing, but notice that unlike the previous one, this one needs at least 2 times differentiating, twice using the L'Hopital's rule before you actually get to this point where you can get a limit of 0. So depending on the problem, you could go on longer than other problems. All right. So that brings us to the end of the indeterminate forms and using L'Hopital's rule to find the limits of expressions.